All right, let's get right into it. If you're currently cramming for your DAP2 exam, you are in exactly the right place. Today's explainer is all about bypassing the fluff and giving you the high-yield quicksort concepts you actually need to know. We're going to tear this algorithm down, look at exactly why it can completely break down on you, and then precisely how we fix it to hit maximum efficiency. So, here is our roadmap for today. We'll start with part 1, intuition, the coin trick. Then 2, formalization, divide and conquer. Next is 3, the threat, worst-case complexity. After that, 4, the solution, randomized average case. And finally, part 5, the proof, information theoretic bound. Let's jump in. Part 1, intuition, the coin trick. Before we look at the math, we really need to anchor your mental model with a physical analogy. Picture this. You've got 100 mixed coins just dumped all over a table, right? And you need to sort them by value as fast as humanly possible. Now, scanning the entire table for the absolute smallest coin and then hunting for the next smallest, that is agonizingly slow. Instead, we use this little physical trick. You just pick one random coin as your baseline, your pivot. Then you quickly divide the rest of the coins into 3 separate piles, those that are smaller, those that are equal to your pivot, and those that are larger. By repeating this process recursively for the smaller and larger piles, you'll see sorting just happen automatically. It's so much faster because you aren't hunting for that absolute minimum every single time. Moving on to part 2, formalization, divide and conquer. Let's translate that physical intuition into the exact terminology you're going to need to write down to get full credit on your exam. Okay, you absolutely need to memorize these definitions because this is the core DNA of the algorithm. Quicksort operates on what we call the divide and conquer paradigm. You are recursively breaking the sorting task down into smaller and smaller subtasks. It works by picking a pivot element, we'll call it L1, and applying Dijkstra partitioning. All that really means is you're taking your data and separating it out into a K-list for the smaller elements, an M-list for the equal elements, and a G-list for the larger ones. Simple, right? It sounds like a beautifully elegant system, but, just when Quicksort seems flawless, we have to pause and ask the most critical question, the one that determines real-world runtime efficiency, and honestly reveals a hidden trap. How many comparisons does it actually make? This brings us to part 3, the threat, worst-case complexity. And listen up, because this is the exact computational trap your professors are going to try to catch you on. You have to understand what happens when the algorithm is fed a uniquely bad input. And the ultimate trap? It's an already sorted list. Seriously, if you feed a standard deterministic quicksort a perfectly ordered list, and it just defaults to using the first element as its pivot, your K-list, the list of smaller elements, is just always going to be empty. So the pivot isn't actually dividing anything. It's just slowly chipping off one element at a time, forcing the algorithm to compare every single remaining element. It's a complete cascading failure in efficiency. And this massive formula right here exposes just how heavy that computational weight gets. N times n plus 1, all divided by 2. This gives us the exact worst-case comparison count. It proves that the workload scales quadratically, making it an absolute O of n squared disaster. If you're trying to sort a massive dataset, O of n squared is practically a death sentence for your runtime. Thankfully, we can fix this. Part 4, the solution, randomized average case. Let's guarantee some stability here. Enter randomized quicksort, or rquicksort. The fix for this glaring vulnerability is actually incredibly simple. We just swap the first element with a random element before we partition it. That artificially creates a random permutation. Basically, by just randomly selecting our pivot, we take fate out of the equation, break that deterministic vulnerability, and make sure that bad inputs, like those already sorted lists, don't ruin our runtime. When you see the two realities of Quicksort side by side like this, the choice is pretty obvious, right? We're contrasting that dangerous O of n squared deterministic worst case directly against the much smoother expected O of n log n curve of the randomized average case. This smooth, reliable performance is exactly why Quicksort is so incredibly dominant in practical programming today. Okay, final section, part 5, the proof, information theoretic bound. Because just stating the runtime is definitely not going to be enough for a university exam. We need to prove mathematically why randomized quicksort behaves so well, using those O-calculus tools from your notes. Visualizing this math is actually super fascinating. Take a look at this chart from your lecture notes. It shows how the expected number of comparisons relies on the nth harmonic number. Notice how that stepwise function just seamlessly scales down to perfectly mirror a logarithmic curve? It's really beautiful when you map it out. So, translating that visual into rigorous math for your test, your source material states that the expected number of comparisons is less than or equal to 2 times n plus 1 multiplied by the harmonic number h sub n. And since that harmonic number bounds to O of 1 plus log n, our expected comparisons formally scale down to roughly 2n log n. All right, so here are the ultimate bullet points you need to sear into your brain for the exam to tie all of this together. First, all comparison-based sorting algorithms are bound by an information-theoretic lower limit. Second, that absolute lower limit is exactly omega of n log n, period. Third, randomization completely saves Quicksort, allowing it to asymptotically hit this optimal mathematical floor. Which means, finally, no comparison-based algorithm can be fundamentally faster than this. Good luck on your exam, guys. You are now fully armed with the intuition, the formal definitions, the worst-case traps, and those rigorous mathematical proofs you need to absolutely crush any Quicksort questions they throw at you. But, while you're celebrating your perfect score, maybe ask yourself this. If Quicksort hits the absolute speed limit for comparison algorithms, does the future of sorting lie entirely beyond comparing elements at all? Maybe things like counting sort or radix sort will be the next big topic we tackle. Until then, keep studying hard and stay focused.